All right. Welcome back, everyone. Hopefully you had a chance to join the earlier sessions and enjoy the lively discussions. So in this session, we hope to dive in deeper into the semiconductor manufacturing process to better understand the environmental impact of these, wafer fabrication process, and really discuss the potential challenges and innovation opportunities in the semiconductor manufacturing, specifically related to water, energy, and materials. So the first speaker today is Lars Ragnarsson. Lars is a scientific director at IMEC, and he will talk about the environmental footprint of logic CMOS technologies. So Lars?
Thank you. Yes, so my name is indeed Lars Ragnarsson. I will discuss the environmental footprint of logic CMOS technologies. This work has done together at IMEC in Leuven, Belgium. Brief outline, I will have a short introduction, put some context on this, and then I will discuss how we are including sustainability metrics in technology pathfinding, and what the environmental footprint of logic CMOS technologies is according to these studies, and then provide some conclusions and perspectives. So first, what is the ICT or IC footprint? Actually, it is a very large one because the digital world contains everything from chips and integrated circuits to edge devices, user devices, to distributed data centers up to the centralized cloud. So actually, it's a very big beast, and it has quite a substantial carbon footprint and impact on the environment. The data centers can be divided into different kinds of data centers with different sizes and different impact, and that goes for the user equipments as well. We should not neglect the network, which has quite some contribution here. There's a lot of traffic between the clouds, between the distributed data centers and user devices. But we have two things to consider when we manufacture these devices, when we manufacture the servers and the cars and whatever, we have some manufacturing footprint. And then there is the power consumption in use. And depending on what kind of device we are looking at, these two, the division between these two is very different. So if we start looking at the data centers, actually the usage is completely dominating. So you see here 99.98% of the carbon footprint is because of the usage. The production is not even visible on this scale. On the other hand, when we look at smartphones or laptops or connected TVs, devices which are quite complex and a relatively short lifetime, then the production dominates. So you see over 90% for a smartphone. And inside those devices, if we look at what is actually contributing the most, we see materials and the integrated circuits are the two biggest contributors. In another study, which is more recent from Gupta et al., they looked at the Apple carbon emission for the full family of Apple products, and what they saw is that 75% of the production of the footprint is the production. So the integrated circuits is actually the largest part of that. Now, if we then compare different kinds of mobile phones, so this is a survey of 9 LCA reports that are publicly available. We see a very wide range of values for different phones. We can note, if you look at the production years here, that overall the more advanced phones, the newer ones, have much higher carbon footprint, and the black part here is the manufacturing. So you can see that that clearly dominates the overall footprint. You can also see that some devices, like the Fairphone, which is designed to have as low as possible carbon footprint, is indeed better if you compare to devices which have manufactured about the same time. Now, when you see such a big discrepancy, you wonder, is it real? Is it really true that there is such big differences, or is it the way that people count? How do you actually get those numbers, and what is behind those CO2 emission values that the companies are reporting? And if we take a little bit broader view, and we see what is the actual complete emissions from the ICT sector, and that actually includes also the entertainment, so streaming of video, etc. We see a very wide range of values, even if we look at today's emissions, so ranging here from below, say, 0.7 up to maybe 2 gigaton CO2 equivalent, depending on what publication you look at. And if you then extrapolate this, you see that the range is enormous, anything from 50% reduction to over 300% increase by 2030. So what is the cause of this uncertainty? Well, first of all, many of these studies are based on limited and aged and or incomplete data sets. The definition of ICT is actually not really standardized. Some includes TVs, some includes even old telephones and things. So it's really a broad range of devices that you can count. So it's difficult to really compare. And then some technologies and applications, they fade out and there are new ones coming in. For example, Bitcoin mining is not included here. And we know that that has quite a large carbon footprint. And in the future, it's just anyone's guess what the next technology or application will be and how it will impact the climate. So we can really not trust any of these projections. If it's going to reduce or increase, it's very difficult to predict. And furthermore, if you look at the distribution between different type of devices, you can also see that there is a variation. So in some cases, the user devices are completely dominating, and others, it is more distributed between them. So what will help is to have better data, and that's what this work is about. We focus on the integrated circuit manufacturing. And of course, there is a lot of concern around the climate change and pollution and resource depletion. So there is a lot of need here. We need to do things to make the semiconductor industry aware and improve on its impact on the climate and on the planet. There is, because of this, also going to be a lot of impact on the business continuity. There are regulations coming that will make it more difficult to get around. And there is quite a lot of existing know-how and efforts in this area, but not so much inside the semiconductor manufacturing, more towards the environment, health, and safety. So the data that I showed before is actually based on lifecycle analysis data that is somewhat, in most cases at least, limited and outdated, because the published data that is available is from around the 32 nanometer node and published in 2012. And that is quite far away from where we are today with our advanced technologies. And finally, these metrics are not included in the technology pathfinding, meaning you do optimization of fabrication with one thing in mind, actually that's to improve on the power performance and area scaling of the devices to make them more efficient, but you do not take the environment cost into account. That's what I'm going to talk about now. How do we include these sustainability metrics in the technology pathfinding? Let's just quickly look at the CMOS technology evolution. It's a quite fantastic evolution, I have to say. So in the happy scaling area, the gate lengths and the metal pitches were scaling very quickly. Eventually, it started saturating a bit, but still the scaling continued. And by making innovations in terms of materials, innovations in the silicon itself, coming up with new architectures like FinFETs, and now eventually into nanosheets, we have been able to continue the scaling and make more and more sophisticated devices. A lot of this is depending on the lithography, which has gone from 365 nanometer down to what today is EUV, and eventually we think high NA will be introduced. Now, this is a very complex task. So if you look at CMOS today or any kind of memory device or whatever, actually you go all the way from laws of nature where chemistry, physics, and thermodynamics play their role, all the way up to system specs where you care about the power performance area, and in this case also sustainability, and anything in between. Now, you cannot build a system with actually knowing a lot of the things below it. That's where the design technology co-optimization came into play some time ago, where you do the module integration of the technology, the physical layout, and the logic design in a co-optimization way. And by doing this to optimize the standard cells, taking the technology into account, you can get a more efficient system. Now, to get over things like the memory wall, a 3D SoC partitioning, or backside power distribution, you need actually to broaden this further and do the optimization all the way from unit processes up to the package system. So this, of course, is a very big task for any company to do, but it's important to go ahead. Traditionally, the pathfinding and design technology co-optimization was focusing on the power, performance, area, and cost. So these are the foundations for Moore's law. And what we are doing now is proposing to add the environmental score to that. So we call this PPACE. And the E in this includes a lot of things like the electrical energy, greenhouse gas emissions, water use, raw materials, waste, and chemistry that are used in the production. These all, to some degree, contribute to carbon emissions because there is some energy needed to produce the raw materials, there is energy needed to do get the chemistries, etc. And all of these contribute to the carbon emissions. Of course, there are other things to be concerned about here. Fresh water depletion, semiconductor manufacturing uses a lot of water, acidification, ecotoxicity, and ozone depletion, etc. There's quite a lot of things that need to be taken into account as well. Now, today, I'm going to focus mainly on the carbon emissions. We look at the water usage just as well. So these three items is what I will focus on in this presentation. So in an overview slide, we do the new node pathfinding by exploring new devices and designs together with the technology definition to make those devices. We evaluate those type of devices in the power performance area using different kinds of modeling and building them in the fab. And then finally, we look at the cost of that manufacturing and also the sustainability of it. To do that, we use a lifecycle analysis, and we base that on our process flows that we have, which have a lot of process steps that are coupled to different tools and recipes. And by doing that, we can then estimate what the electrical energy is used and how much of the gases we are using. Then we use standards to actually convert the electrical energy into the CO2 equivalent based on an assumed energy mix. And in the gas case, in the direct emissions, we use the global warming potential for the different gases and make assumptions on abatement and utilization in the chambers. And then finally, we can add these two up to have most of the emissions from the process. This slide is just introducing some of the differences between the different technologies. I should point out that in IMEC, we have a node name which is slightly different from the nodes in the industry. You see that for 28 down to 10, it's the same as most industries refer to them. But from then on, we were a little bit optimistic, so our nodes are a little bit higher in the name. So IN5, for example, is more like the 3 nanometer node today. Yes. Okay, so let's first look at the classic one, power performance area scaling. So going from a 28 nanometer node now down to 3 nanometer, we see that there is progressive area scaling. We are improving node to node on the area scaling. So by using these advanced concepts of making FinFETs and then nanosheets, etc., we can continue the area scaling. And furthermore, the performance is also improving. So if we look at the active power versus the frequency, we see that the frequency is improving node to node if we look at an active power, constant active power, or equivalently at a given frequency, if we look, we see that the active power is reduced from node to node. Now the question is, what is the environmental footprint looking like? First, we need to look at the equipment and see how much power it's using and what the throughput is. We see here quite a wide range of values. These are for different types of tools for the different areas as mentioned here, going from CMP, FP down to wet processing. And the same tools have then a wide range of throughput values. point is standing out, and that's the EUV, which is using quite a lot of electrical power, 1 megawatt, compared to the previous technologies using immersion, which was more like 100 kilowatt per tool. At the same time, the throughput for EUV, at least in the initial states, were not that great. So that caused an issue, and I will show that actually today it's less of a concern. The slowest steps are based on atomic layer deposition for very thick layers. So this is actually covered in the PVD part. And also EPI is a very slow process. Now, there are not so many of those, so that has a little bit less impact than lithography, which is used a lot in the process. Just a very quick word, maybe a bit too technical, but about how we do patterning. So actually, using immersion lithography, there was a lot of tricks that were used to enable getting very advanced and tight pitches by doing multiple patterning steps. So you do litho etch repeatedly, or even 3 times to get to a very high dense pattern where the immersion could not get to one print. Self-aligned multiple patterning is similar, where you print something big and then you grow spaces on it and you cut these to enable small feature sizes, and you can do that in quadruple patterning. Now with EUV, we can replace these by single patterning, and eventually we need to go to double patterning also with EUV. Now the question is, what happens then in terms of the carbon footprint, because EUV has this very large electrical energy need. And in fact, if the throughput is high enough, so here you see 100 wafer per hour, it's equal. So what I'm comparing here is self-aligned quadruple patterning with an electrical energy need of 15 kilowatt hour per wafer. You see here that deposition is really dominating, and that's because you need to deposit a lot of layers and then etch and then print and then deposit and etch and print and so forth. Whereas in the EUV case, the lithography is dominating and the rest is much, much smaller. So if your throughput is over 100 wafers per hour in this comparison, it's clear that EUV is actually better. And if you look at ASML's most advanced tools, it's very clear that the throughput is beyond 100 wafers per hour. So this looks quite good. EUV seems to actually save energy rather than the other way around. Now the complexity is increasing quite a lot. If we look at the different devices that we're going, different technologies. So in 28 nanometer up to IN3, we see an increase in the number of back-end of lines layers, and we have each of these layers getting more and more energy costly to produce, and therefore our total energy use is increasing quite dramatically. So we see node to node in some cases where we have to introduce very advanced block patterning, etc. We see increases in the order of 40 or 30%, which can be quite problematic. We also see that if our throughput for EUV is high enough, we actually are neutral. So in this case, we have assumed 110 wafers per hour, and then we see very similar. Now, if we assume a little bit more optimistic values, we will then see that the EUV is actually better. So if we then just compare at a high level the process complexity, here you see the front end of line in blue and light blue, the back end of line, and in brown, the middle of line that came into play in 20 nanometer node. We see that the back end of the line is dominating. That's because of all the metal layers that are introduced. And the increase in complexity is around 2.5 times. Here we have assumed 3 VTs in the front end of line. And in many new technologies, there are actually many more VTs than that. So that will increase the complexity. But for simplicity, we just assume that there were 3 threshold voltage for each technology. This converts into an electrical energy increase of around 3.5. Here again, we have assumed 100 wafer per hour throughput for EUV. There's one thing missing here, and that's the facility energy. So we have counted only the tools, what energy they are using, but not how much the facilities that actually produce the vacuum and pumps the systems and provide the high pressure air, etc. And to do that, we made an assumption in this case that, and this is based on other studies, that it's about 40% of the total. So that's this light blue added on top. And then you see the overall energy need per square centimeter for the different technologies. If we compare that to what ITRS set out some time ago in 2016, as I think we are actually from the 8 nanometer node and onwards quite significantly above that target. So there seems to be some need to improve on the energy efficiency here to stay below this target. Furthermore, the water usage is also increasing quite a bit. We see going from 6 liters per square centimeter up to more than double of that, 14 liters per square centimeter, because of all the different steps that needs cleaning, etc., in the more advanced nodes. Again, here, EUV shows up to be improving the water usage simply because we use less steps. Finally, we can convert this into the carbon footprint by assuming some electricity mixes. So here I have 4 examples. The first one in purple here is more or less the Chinese electricity mix. In green is more or less what you would have in the US. And you see here the increase is going from 0.7 or so up to over 2.5 in the worst case, and between 0.2 and up to 1 kilo per square centimeter in the better case. It is very clear that there is a strong increase because of the increase in the complexity, but going towards more renewable energy can save a lot. So that is clearly one of the key items here. Moving fabrication towards renewable energy will save a lot of the issues. What we can say here is that for example, 40 nanometer, there is about 240 to 560 kilo per wafer of CO2, depending on electricity mix. And this corresponds to about 65 to 85% of the total CO2 equivalent emissions. Then you might ask, what is remaining? And that's the direct emissions. So if you look at the gases that we're using in our processing, there is a wide range of gases that actually are very harmful in terms of global warming potential. For example, SF6 is 23,500 times the global warming potential of CO2. And CH4 is not that bad, we use quite a lot of it. And NF3 is also used abundantly in processing to clean chambers, etc. And it's 16,000 times worse than CO2. So because of that, actually, all of these gases adds up, even if in this case we have assumed, as you can see here, abatement factors of 0.9. So 90% of these gases have been removed from the exhaust. And still, these are the numbers that we see. So to actually get to below the targets of the ITRS in 2016, we would need to go to 99% NF3 abatement, which is very energy demanding and will also cause increase in the emissions because of the abatement system. So here I think there is a lot of opportunities actually for ventures to see where can we do something to improve on this situation. The new gases maybe that can be used, new ways of getting rid of them at the exhaust, etc. So I think this is a good space to play. Finally, when we look at how normalizing these metrics to an area and to the 28 nanometer node, putting that at 1 year, and then looking how it progresses node to node, we see that we are getting improvement in area scaling. It is getting better for each node, yes. And we do see that the devices are getting faster. So there is an improvement compared to the 28 nanometer. We also see that the cost and the environmental costs are also improving, so node to node. But that's when you normalize it to a device. Now, the problem is, of course, that we tend to just use more and more devices. So in the end, this will not be representative in the end, because the system complexity is increasing for each node. That means that the overall manufacturing energy per die will increase. So in conclusion, we are using DTCO, Design Technology Co-Optimization, and including sustainability there to estimate the environmental metrics in an early phase of technology definition, to benchmark different integration schemes, identify key process steps, or draw sensitivity analysis to specific parameters. Like in this case, I looked at EUV. The environmental footprint of logic CMOS technologies, we see that node to node, it's increasing electrical energy, water, and greenhouse gas emissions per wafer. And this increase is due to the increasing complexity. The number of steps are increasing. We have more complicated processes that use to improve the scaling. We have more metal lines, we have more patterning and more low throughput steps. And we find that EUV is more energy efficient when throughput is above 100 wafer per hour. And we find that having an environmental score in technology pathfinding would be crucial in order to make environmentally wise choices towards more sustainable future technologies. In fact, to address this, IMEC is initiating an activity towards its ecosystem to provide more insight. So this is a program that you have recently started. And with that, I'm finished. Thank you so much for your attention.
Okay. All right. Thank you very much, Lars. That was a fantastic talk. Really appreciate you kind of setting up the baseline and really sort of quantify what are the energy and materials consumptions during the semiconductor manufacturing process. For those in the audience, we will try and make the video recordings of all the sessions of today available later today or tomorrow. So you can focus on, listening in and don't have to worry about missing some of the important figures and numbers that Lars presented earlier. So we have a few minutes for a quick question, Lars. Most of the audience here are based in North America, so I'd be curious to hear, maybe you could elaborate a little bit. What are some of the European initiatives that are relevant to semiconductor sustainability, and related to that, what are some of the sustainability projects, specific projects that IMEC is working on?
Yes, so the EU has a lot of funding for the industry in general. There's a lot of calls out now because of the Green Deal, and most of these have sustainability in the description. So we actually submitted one yesterday where sustainability is part of it. So I think there is a lot of opportunities there to actually get some funding for activities. In IMEC, as I mentioned, we have started an activity. We call it Sustainable Technology, Semiconductor Technologies and Systems. And we are there looking at what I just showed, assessing technologies, and we're going to work with our technology providers, our suppliers, our equipment manufacturers that we have in-house and that we work together with to see if we can find new solutions, to come up with new recipes, new processes, and new ways to save on the environmental footprint of the manufacturing.
Yeah. So I'm looking at the chat box. There are some questions all around EUV. Since EUV is pretty much it's a monopoly by ASML. I don't know, Lars, if you're in a position to comment. What are they doing to make it more sustainable?
Yeah, I don't want to say too much. I do know that they have a very aggressive roadmap towards reduced emissions, and they're doing the best they can, I think, to improve on the energy efficiency of their tools. But I don't want to say too much more than that. But they have been working together with us on this project as well. So if you look at the publication that we had at IEDM, you see that the ASML is actually co-author on that one. So
excellent. Okay, good to know. With that, I think we'll move on to the next speaker. So next up is Dr. Andreas Neuber. Andreas is a Senior Director at Applied Materials, focusing on fab environmental solutions. So he will talk about some of the technologies and methodologies related to resource efficiency, energy, and water. So welcome, Andreas.
Hello. So my presentation today want to show some examples how a fab can go to carbon neutrality. We have seen that manufacturing actually plays a very important role in the carbon footprint of our industry. And we want to show here in this presentation what are the possibilities, how we can achieve that in the time frame what companies have recently announced between 2025 and 2030. Mhm. Apologize.
All right, looks like there's some technical difficulties with Andreas. Maybe, Catherine, if you're ready, we can get you started. Catherine is the executive director at EMD Electronics, Merck KGaA, Darmstadt, Germany. So she will be talking about semiconductor sustainability from a materials supplier perspective. Catherine?
Hello, thank you, John, for the kind introduction, and I will speak 30 minutes before, and hopefully Andreas will be able to join us after my talk. Earlier today we heard from industry leaders about their sustainability goals and their strategies, and we heard from the venture community about their investment strategies as well. And now I'd like to take the conversation in a different direction and share with you a material supplier's perspective on how we can make electronics more sustainable. So, first I will give you a brief introduction into who EMD Electronics is. Then I will share with you a few ways that materials innovation is actually enabling more energy efficient chips. Then I will discuss some of the environmental benefits as well as challenges faced by the electronics industries, and where we as material suppliers, as entrepreneurs can, where innovation is needed to really help make semiconductors more sustainable. So EMD is more than 350 years old. We are one of the world's oldest technology companies. And science is at the heart of everything we do. We have more than 58,000 employees. We generated more than $18.5 billion in revenues last year. But we're not maybe as well known in the US as we would like to be. So we consist of 3 different business segments. So in the US, our healthcare business is known as EMD Serrano. Our life science business is known as Millipore Sigma, and our electronics business is known as EMD Electronics. But we don't own the Merck trademark in North America. So outside of North America, we are known as Merck. So just want to explain the naming convention there. But in terms of our sustainability ambitions, we have 3 overall corporate goals, right? So the first is that by 2030, we will achieve human progress for more than 1 billion people through sustainable science and technology by making a positive impact on human health, as well as by 2030, we will integrate sustainability into all of our value chains and our supply chains. We need to make them transparent, and we need to secure our social license to operate in all regions. And finally, by 2040, we will achieve climate neutrality and reduce our resource consumption. And we will do this by minimizing our climate emissions, our emissions that have a negative impact on the environment, as well as reduce the intensity of the water and resources we consume during our manufacturing processes. And these goals reflect what EMD is standing for and its contributions to society as a science and technology company. So EMD Electronics is one of the world's leading material suppliers in the semiconductor industry. Through our acquisition of Versum Materials, we now provide solutions for every step of the IC manufacturing process, as well as equipment and on-site services. Our acquisition of Intermolecular enables us to build prototypes and optimize integration schemes. It is our extensive industry experience and broad process knowledge that gives us insight into both the benefits and challenges faced by the semiconductor industry. So over the next decade, and Lars alluded to this too in his talk just before mine, is that our industry will continuously deliver smaller, faster, and higher performance chips, while at the same time creating more energy efficient devices. This industry, we refer to this as power, performance, area, and cost optimization, or PPAC. Materials innovation, along with chip design, are key enablers for PPAC. So shown on this slide is a high-level summary of the technology roadmap for logic, DRAM, and 3D NAND. And if you were to deep dive into the advanced logic roadmap, you would see that many of these technology inflection points are being driven by the need to not only reduce power consumption, but at the same time, maximize chip performance. So one example of a near-term transition is this change from FinFET to nanosheet. And this will only happen by new materials being provided, such as selective etchants or materials that can enable threshold voltage tuning as well. But these chips made with nanosheet transistors will enable more energy efficient data centers and more high performance computers. So another example of how materials are reducing power consumption while boosting performance can be seen in the DRAM roadmap, where there will be a change where high K metal gate transistors are going to be adopted in the peripheral logic circuits. And finally, if you go to 3D NAND, new materials such as molybdenum are required to help reduce RC delay, again, optimizing power consumption. So these energy efficient chips will enable global connectivity and digitize many processes that we experience in our daily lives. And there was a study done by GESI, the Global E Institute, and they analyzed this potential benefit, and they found that basically by 2030, the ICT systems could reduce global emissions by 12 gigatons per year. And in fact, they can save nearly 10 times more emissions than they produce. And the way they can do this is by this decoupling of GDP growth from CO2 emissions. This digitization of our lives, which has been accelerated by COVID, right? We are now teleworking. We're having a remote conference. We have smart agriculture, telehealth. All of these things are causing this decoupling. Where traditionally we had 1% of GDP growth drove nearly a 0.5% increase in CO2 emissions. This should not happen. So we will achieve GDP growth, but not the same amount of CO2 emissions. And while this is all well and good, for those of us who've been in the industry I'm over 20 years in this industry, there is a dark side to the electronics industry. And this is really what I want to talk to you about today, about how we as innovators and entrepreneurs can help resolve this and make electronics more green. So Silicon Valley is the birthplace of semiconductors, and yet we have the most Superfund sites of any county in the US. I'm based here in Silicon Valley. We have 23 Superfund sites registered with the EPA. The Atlantic Monthly, the New York Times, the Wall Street Journal, you can Google this. There's many articles about all these Superfund sites and what their impact has been on our community. So for example, we have the Triple site, which is one of the more famous ones. It's in Sunnyvale. There's a map shown here on the slide. It's named after 3 companies who started it, Philips, AMD, and TRW Microwave. This site, these fabs were built in the 60s and in operation. And what happened, and this is a common issue that's happened here in the Valley, they stored trichloroethane in underground tanks, and they leaked into the soil and the groundwater. And over the next following 2 decades, they kept leaking. You know, the ground is slightly tilted towards the bay. And as you can see, the TCE spread underneath hundreds of homes and 4 schools before they started to clean it up. Now, why should we care? What's wrong with TCE? You know, it can cause abnormalities in your liver and your kidneys and your heart. It's not good for pregnant women to be in their house and have plumes of TCE kind of permeate up through the soil. If you go to many of these schools, they have extra ventilation systems and air monitoring in there. So, and it was also banned by the Montreal Protocol. So this is part of the legacy. You know, semiconductors has created a great innovation and job engine in the Valley, but it's also left behind, you know, not such a great legacy of chemical contamination. Another big issue that we as an industry, I think, have the power to change is this e-waste. In 2019, there were 54 million metric tons of e-waste generated per the United Nations. And if you dig deeper into that, you can see that Americans in 2014, we threw out more than 400,000 mobile phones a day, right? And that translates into more than 150 million phones a year. You know, this combined with this accelerated digitization of our lives, we're on track to generate nearly 75 million tons a year of e-waste. So let's dig a little bit deeper, right, into what's actually happening with the chemicals and the waste that's being generated by semiconductor fabs in the US, right? So there was a paper published in 2018 by Shen et al., where he and his team, they went and mined the EPA toxics release inventory to find out, well, how are semiconductor fabs handling waste from these 7 common chemicals that are pretty much used in nearly every fab around the world? The authors of the paper found that the waste was either released on-site or off-site without any treatment into the environment, right? They found that some was treated on-site or off-site and then released. And what they mean by treated was it was incinerated or it was oxidized. And then some waste was recovered. And here what they mean by recovered was it was actually captured and then incinerated to create energy. But very little waste was recycled, right? The paper is a very interesting paper. I suggest people go and read it. It actually lists semiconductor companies by names and locations and ranked them from best to worst. The paper also explicitly stated that several companies, again, were discharging directly into the environment without any treatment. 2 companies, one located in Santa Clara and one located in Milpitas, were actually releasing 100% of their HF waste without any treatment. And this despite, you know, our county having a Office of Sustainability that's been in place since 2010. So what can we do to increase the sustainability of electronics? Sure, we can buy carbon credits to offset our plants. We can make our logistics green. We can have zero waste offices. We can digitize our plants, minimize energy consumption. In my mind, these are all table stakes, but we need to take this to the next level and really make our processes more circular. So I'm going to discuss 3 different semiconductor process flows in the next couple of slides, right? Talk about the current situation and ways we can innovate to make it more green or more circular. So let's first look at thin film deposition, right? And these are just very simple pictures, you know, they're just very straightforward process flows. And as you can see, when you're wanting to deposit a film, you flow precursors and reactants into a deposition chamber. You know, very rarely is 99% of that precursor consumed. Instead, a lot of these unreacted precursors and reactants flow through the vacuum pump into the gas abatement system, where it's incinerated and then wet scrubbed, and then the wastewater goes to the water treatment system. So we're basically incinerating these very expensive, precious chemicals that we spent all this time and energy to create and purify, right? So what can we do as innovators and material suppliers to make this process more green? So in terms of energy consumption, if we can focus on developing more low temperature deposition process, that will reduce your energy consumption during the process step. Also, we need to optimize the reaction efficiency. You know, that can come from chamber design, can also come from the design of the precursor, but ideally you want a highly reactive process that generates innocuous byproducts. We want these precursors to be non-toxic. And ideally, and this is again a step change in our industry, we need to minimize the use of virgin raw materials. We need to be more open to taking in recycled and recovered raw material streams rather than focusing on virgin raw material sources. And, you know, we have wonderful chemists in this industry, but no matter what, you're not going to make a reaction be 99% efficient. There's going to be sometimes half of your precursor flowing all the way to your abatement system just to be destroyed. We need to begin to recover these more, to purify and put them back into our supply chain. This is not a new idea. You know, back in the early 2000s, when ruthenium was first being explored as a potential interconnect candidate, ruthenium is very expensive, so there was an economic driver, and people talked about ways to recover it. But the industry, we're not doing that. We are simply abating and sending it down the waste stream. Another area I want to talk about is CMP, which was also highlighted in Lars' talk. CMP is one of the largest producers of water waste. What CMP is, it's a process used to planarize the surface of a wafer prior to lithography. It's very crucial to creating advanced chips. And the CMP process uses a slurry, which consists of nanometer-sized particles, chelating agents, and surfactants. And then after you do the process, you then use a post-CMP clean, which often includes surfactants as well. Now, what makes this process so hard is the waste stream it's complex, right? It's a mix of dissolved metals, fine particles, again, these chelating agents, inorganic ions. It's one of the more complex waste streams that you have to handle in the fab. But there's things we can do as an industry to make this greener. We need to prioritize the use of non-toxic corrosion inhibitors, surfactants, and chelating agents, or simply, you know, raw materials that are more compatible, that maybe biodegrade down into the system into innocuous chemicals. And I think we really need to revisit yet again what we can do with the abrasives in this waste stream. There have been examples of some experiments by other fabs in the past where they looked at, you know, can we recycle the abrasives from some of these higher solid content slurries, or sometimes the abrasives are so expensive that it makes sense financially. But there's just this real hesitancy to make it a more circular process. The only area I know of where a slurry is reused is in wafering, but I don't know of any being actively used in high volume manufacturing. And this applies on both legacy nodes as well as advanced nodes. And finally, you know, wafer fabs use millions of gallons of water a day, right? And we need technologies that can enable water to be reused throughout the fab. And really, we need to target zero water discharge. And again, there was some great, you know, I think Intel mentioned earlier today some of their efforts they're doing so they're actually putting back more water than we take. That's fantastic. There are hundreds of fabs all over the world, and I don't think everyone is doing that level of effort. We need a mindset change. So the last process I want to discuss in detail is really lithography, right? So this is where we do the patterning of the wafer. And I'm not even really going to talk about EUV. That was already covered by Lars. I'm going to talk more about the materials. And if you look at photoresist, a photoresist consists of polymer solvents and these fluorinated photoacid generators that are known as PEGs. These PEGs, they are on the list of PFAS materials, and you can see this summary chart here. And what are PFAS materials? These polyfluoroalkyl substances, these are these forever chemicals, right? They have extreme persistence in our environment, as well as bioaccumulation potential, as well, again, also global warming potential. Once you release these fluorinated PEGs into the environment, it is very, very hard to clean it up. And the industry, we need fluorine-free PEGs, right? Not just for advanced nodes, but also for legacy nodes. And we need to be open to making this change and adopting these new materials. I want to give a shout out to SRC. They have active projects in this space, not only to find fluorine-free PEGs, but also they're looking for technologies that can remove these substances from the environment once they've already been released. And then, you know, further on in the process, we need a developer. One of the most common developers is TMAH, tetramethyl ammonium hydroxide. I mean, this chemical has killed people in the fab. It's very, very toxic. We need to find alternatives to that. So we need non-toxic developers as well as removers, right? NMP is one of the benchmark solvents that's commonly used. And while it may be a low ecological hazard, it does pose reproductive and developmental risks for humans. So the good news is that, the industry is starting to change. And, it was really great to hear in the first session this morning, all the effort being made by a lot of the industry leaders. I'm just going to talk briefly about two such, I think, efforts in the right direction. And one of these was already kind of covered earlier today by Intel. But if you look at the Intel's publicly available sustainability report, you can see the amount of progress. They've made tremendous progress since 2015, right? They've increased their rate of waste recovery basically to 40% and doubled the overall amount of reused fab waste. And if you look at their most recent sustainability report, they reused, recovered, or recycled 180,000 tons of manufacturing waste. And how they did this, some examples, they recovered the waste from the copper plating baths. You can electrowin out the copper and recover it and then repurpose it. They also recovered their sulfuric acid and then reused that in their wastewater treatment facility. And then if you think about what's going on in Taiwan, Taiwan is an island with limited water resources, yet it is home to the world's leading foundry, right? And so they've had on and off droughts. 2020 was particularly difficult. No typhoons hit Taiwan in 2020, and this led to the worst drought in 56 years. TSMC was reactive. They built a water recycling plant that will meet almost half of its daily need for water, and this is planned to go online by the end of 2021. So, the second area or the second topic I think is ripe for innovation for startups, and it's an absolute need, is this e-waste situation. As I mentioned earlier in my talk, right, we generated 54 million tons of e-waste globally last year, but only 17% of that e-waste was actually recycled. With Europe leading the way, right, 42% of e-waste was recycled. In the Americas, we recycled less than 10%. But we have to really ask ourselves, are we really recycling this e-waste, or are we just exporting it? And this map here came from the World Economic Forum. And what it clearly illustrates, it shows that the countries that make the most e-waste are exporting it to these countries that are hardly generating any e-waste. And it's quite heartbreaking because a lot of these developing countries don't have EH&S legislation, they don't have PPE, there's child labor law issues, and we have to take care of our own waste. We can't export our problem to somewhere else. But again, this is a venture forum, we're here to make money. Why do we care? Now, if you go back and dig through this data from this UN report, they value the amount of waste, the e-waste that we threw away, at $48 billion. They're saying you're just putting $48 billion back into the ground. That is basically the same size as the semi-materials market. It's a significant market. If you think about, how many billion-dollar size companies are chasing the semi-materials market, it kind of helps understand, well, maybe this is worthwhile pursuing, right? And why is this waste worth $48 billion? So again, you peel back the onion, you look into the data, and what people have found is that for every million cell phones that are recycled, you can find 35,000 pounds of copper, nearly 1,000 pounds of silver, 75 pounds of gold, and 33 pounds of palladium. And then if you look at, what is in a ton of circuit boards, right? You have this waste, you get your ton of circuit boards. If you could mine it, there is 40 to 800 times more gold in 1 metric ton of ore, and 30 to 40 times more copper in a ton of circuit boards that can be mined, right? So this is an opportunity, right? What we need is low-cost, energy-efficient, non-toxic processes that can mine our e-waste to recover the raw materials and then put it back into our semiconductor materials supply chain. And we need to be open as material suppliers to taking these materials back and putting it in our supply chain. So when you look at the overall electronics life cycle, it's really mostly linear, right? The sourcing, we focus on virgin materials. Yeah, once I'm done with my phone, it's going into a landfill. At least 80% of the phones are going there, right? Globally, right? We need to transform this into a circular process, right? So what can entrepreneurs and innovators and the VC community, how can we make this better? What are the opportunities? Again, from a materials perspective. So when you first go out to make your chip or your electronics device, right, these product engineers, these designers, they need to have at their fingertips or in their mind, they need to have availability of non-toxic alternative materials that are easy to recycle from e-waste. And then when you go into the so they can design in these materials, right? They become POR. And then in the semiconductor manufacturing environment, we need technologies that can enable us to reuse the water and materials, ideally at the fab. We don't want to recover some of our waste or put it in a bunch of metal cans and ship it around the world to be recovered or recycled. Ideally, you would do it on site. It's a smaller footprint from an energy consumption as well, potentially. And then we live in this age of disposable electronics. Again, we're replacing our smartphones every 2 to 3 years. We're incentivized by our phone contracts to do this. We're throwing out more than 400,000 phones a day, right? This is not sustainable. And innovation is needed. And also a cultural mindset needs to change. To create materials, we need to extend the product lifetime, but also these cell phones and other devices, we need to be able to upgrade them. So you're not throwing the whole thing away. It needs to be something that is upgradable and lifetime. It could last 10 years or longer. And then the end of life part of the life cycle, in my humble opinion, is ripe for innovation. We need energy efficient, high yield, green technologies that can mine the millions of metric tons of e-waste for raw materials. And then this takes us back to sourcing, right? So the materials that we cannot reuse or recover in the fab, we need to take these back as material suppliers. We need to be open to that, these recovered. We need technologies that can help us recover these materials downstream of the process, that we can purify and reuse as raw materials, as well as taking raw materials from the end of life portion. So we need these purification technologies, but then we need to also apply green synthesis techniques to help us create material solutions, which are then fed into the design phase. And then we go through the cycle again. So EMD Electronics believes that climate protection and energy efficiency will pay off in the long run, both for the environment and for our business. Some of the climate actions that we're taking, we're minimizing the process-related emissions. This is a corporate-wide, and we're cutting down on energy consumption. And we're also purchasing electricity generated from renewable sources. But in terms of specifics, in terms of semiconductor processing, I want to highlight 2 areas that we've made progress on. One is that we've actually launched an NMP-free photoresist remover, and that we have active R&D projects on fluorine-free photoacid generators. I want to thank everyone for your time and attention this afternoon, or wherever you're located in the world. And I want to echo the messaging from several of the other speakers earlier in this talk. It's going to take a village. It's going to take our entire ecosystem working together to co-enable our sustainable semiconductor future. So thank you very much. And I welcome any questions.
Done pushing live.
All right, thank you very much, Catherine. That was a fantastic talk. There were some questions asking about e-waste. I think you had a pretty detailed slide that already addressed that plenty. So let me skip to another question. This is probably a quick one. Do you think there's a need for a better regulation to motivate the industry to shift towards greener alternative materials?
Yeah, yes, I do. I think what we've seen in the past is we tend to ask for exceptions to the regulations and to kick it down the road. And we can't kick it down the road any further, right? I mean, I think the regulations, of course, would help.
Absolutely. I think also it is encouraging to see the industries rallying around this topic, even without sort of the presence of regulation. We're kind of preemptively looking at this already. Since this is a sort of a venture-themed forum, perhaps I will ask you a question around innovation, just real quick. You know, AI technology has come along, and there are many applications, and including AI-based chemistry development, R&D, or material informatics. Can you just share with us sort of your view about how AI technology could make an impact to maybe develop greener chemicals and materials?
Sure. No, thank you for that very timely question. So AI and materials informatics, it's really becoming table stakes for leading material suppliers to create innovations fast enough for our customers, because our customers are also using that as well. But there's two big benefits that I see. One is that, through AI and informatics, you can basically reduce the number of experiments you need to get to the answer, right? So in theory, you can use less wafers, less raw materials to solve the problem, right? So in a sense, it not only accelerates it in time, but also reduces the amount of resources and energy required to create your new offering. But I think another way you can look at these tools is, could you use them to then model how well or how easily they could be recycled or recovered, or their impact on the environment? So to me, there's two areas how this powerful technology such as AI can be used in a positive way for our industry.
Wonderful. Hopefully to give the audience who are working on AI technologies some idea, what they need to be thinking about when trying to apply this technology to the semiconductor material space. So thank you again, Catherine. That was a fantastic talk.
Okay, thank you. Thank you for your time.
I think next up we have Andreas back. So maybe we can just go straight to Andreas' presentation.
Hello. So my talk today should show some examples how a semiconductor fab can find their way to carbon neutrality. Partly, I'm referring to some of the questions Catherine raised here. So I want to talk about the methods existing to approach carbon neutrality in a most efficient way. That means with costs in mind. Are there KPIs which could be used for that process, for driving that process, and for benchmarking between fabs and to other fabs? And what are the typical opportunities, the low-hanging fruits, and the big KMs today? So focus in my talk will be on the scope 1 and 2. Scope 3 is important, and we cover a little bit of it as waste for the water. But I agree that the waste is actually something what you always keep into mind, even if you implement measures to improve on scope 1 and 2. That should not jeopardize your future targets on scope 3. All of that, what you should do very carefully. Semiconductor fab is a very complex mechanism. You have more than 700 steps. You have dozens of different processes. Most of them are running on literally the physical act of what is possible. It's very, very complex, very many parameters, what you need to consider. So you need to break that up, and that's what we are doing. So we break that up, this complete fab, into different equipment, building digital twins. When you have a digital twin, then you are able to start your digitalization, measure, implement signals from the process, bring it up into a measurement, and from there you can run in applications where you implement predictive maintenance or using AR and roll out that to your complete fab. So that's the typical process you need to maintain all the time. So what kind of KPIs you can use to judge whether you are doing a good job or a bad job? So I call the first one resource consumption-based KPIs. So these are very famous, and you have seen a couple of them today in the first two presentations. So how much water per square centimeter silicon, how much water per wafer, how much energy per wafer, etc., etc. So they're easy to calculate. They are relatively easy to compare between fabs and other processes, but you actually never know whether you're good or bad. So they changes over time with progress and tactical changes in the process. So it's actually very difficult to handle them. But you not only have the process itself, also in your facilities, it means in all the technical units around that, you can also use resource consumption-based KPI. Very often that's not even done today. So you can calculate how much energy you need to generate a cubic meter of compressed air, or a cubic meter of nitrogen, or a cubic meter of water. So we are approaching customers to work with us to combine the two to provide a more comprehensive picture of your fab. CMOS 23, which is the standard for measuring the energy consumption of a tool, is using that factors already. They call them ECF, energy conversion factors. That means basically how much kilowatt hours you need to generate to develop other energies, exhaust, process cooling water, etc., etc. And you heard already in the first presentation, that's very important in semiconductor industry because only half of the energy is coming from power itself. Half of the energy is coming indirectly via CDA, via nitrogen into the process. The next step would be to transfer these two type of KPIs in resource efficiency based KPIs. So here you should have actually for your, and that's another point in semiconductor, our fabs are located from Singapore to northern US. And all the climatic conditions around that fabs are very much different. You have islands, you have water availability and other issues. So for each site, actually, you should calculate what are the optimum theoretical minimum and maximum energy efficiency consumptions. So that's another task what you take care for. And the last but not least, you also should look into your individual components. For instance, motor efficiency is a very hot topic. So how you can implement and drive the use of the best individual components in your factory by using KPIs for that as well. So to give you some examples, when certain KPIs would work and when others would not work. So we have certain checkpoints. You can always check how many wafers you have per manufacturing area. And you must know that a lot of our systems, like for instance exhaust, are running all the time. So that means whether there's a wafer process or not, very few of the central facility systems are following that. And here you have both something that you need to watch when you want to benchmark, and also at the same time an opportunity. Because when I don't observe the wafers today with modern IT technologies, I can use them in the fab to adjust my consumption to the actual operation, and I'll show you that sometimes later. So when you have such a resource KPI, which is driven by the mere existence of a tool, then your consumption per square meter manufacturing area is actually the best benchmarking you can take. In comparison, you have other chemicals like Catherine mentioned the process gases or lithochemicals. Since they are so toxic and so hazardous, we would never use them if not needed. So today's equipment have a zero consumption for that kind of process chemicals, which are so toxic when they are not needed. So that means here the benchmarking per square centimeter silicon is better than the benchmarking per area. And then you have utilities like ultra pure water, which are partially, you are using them that way and that way. For instance, for a quick dump rinse in UPW, or a single wafer clean, you would only operate water when there is a wafer present. But for an overflow clean, to keep a reactor protected from other environmental contaminants, then you would run them nearly all the time. So here you have to have parameters have to develop parameters which are more complex. See an example here, a very simple thing like an air separation plant. In an air separation plant, you liquefy air and then you generate the nitrogen and the oxygen out of that plant. You see the power consumption per cubic meter nitrogen as the leading parameter is theoretically around 0.25. And the majority of the fabs you see here are within a certain range in meeting that criteria, depending on geographical. But there are some companies, obviously, who have found a much better technology. And you have other companies who are using outdated or making some mistakes in the operation. So a simple parameter like that energy efficiency per cubic meter nitrogen, can already give you very important hints how you can improve your carbon footprint today. So when you approach eco-efficiency engineering problems in the fab, and when you're looking for an opportunity, the bigger leverage is always when you can improve something on the process or in the associated cleaning. In semiconductor, the cleaning of the reactor is often more complex and demanding, or equally complex and demanding in environmental perspective than the process itself. And then you have your process support areas driving that supporting that process, and everything else needs to follow. When I'm generating here a lot of HF waste, as Catherine showed, then of course I'm ending up in my facility system with a lot of fluoride waste. If I want to reduce that waste, I have actually only a chance when I do that in the process and in the process support itself. So what are examples? Alternative process materials have been already mentioned today many times. Low temperature processes, reactor design, this is how you can improve the process from itself. But once you have installed an equipment in a factory, that alternative is gone. You cannot easily change every other year and throw in a multi-million-dollar equipment and replace it by something else. So the process support area is then the area where you can improve your existing tool base and optimize that in eco-efficiency engineering, with eco-efficiency engineering methods. To show you some example. When originally you had no communication here when there was a wafer running to the support systems, like the vacuum pump and abatement, what Catherine mentioned in the last presentation. If you communicate with them by identifying modes where the wafer are not running, or the wafers are used, for instance, in an annealing process where there are no hazardous gases needed, then you can optimize it, and I'll show you later an example. High temperature process cooling water is another opportunity here. When traditionally we are using a process cooling water set at 17 to 20 degrees C. This water was needed in the past to dehumidify the air in the lithography process. So this is where it was sent. But actually, a lot of the processes are running at 50, 100, up to 900 degrees C. If I could, instead of using a 17 degrees C water, if I could use a 35 degrees C water, I could eliminate a chiller. The chiller is turning the temperature from the cooling tower from 35 to 17, so it consumes a lot of electrical energy. They're actually the biggest energy consumers in the fab. So with that chiller's elimination, by changing its process cooling water temperature, we could actually enable a major change. However, there are many minor details in the factory, like the reliability of electrical components itself, like the customs that you have that cooling materials in contact with clean room air, and you would impact on the clean room air. So the semi-standard has been written this year, but implementation up to now, not this year, last year, but the implementation of that change here in the process is still outstanding. So no fabs are using that in the moment. From the innovation perspective, an area where we can really also make a big change is to recover heat in our process. Now, heat recovery is easy if you have a high temperature, and heat recovery is easy when you have not all these aggressive materials, what we are using in the reactors. Our heat is coming at between 40 and 80 degrees C. Between 40 to 80 degrees C, we can have heat available in less aggressive chemistry environments, but there are not many technical means today which can utilize that low temperature heat sources as big as they are. So innovations in that field, I would really appreciate. This is something I think where you can make a big change in the semiconductor. Of course, you can also go and say, I'm building a reactor out of heat recovery materials, but then you need to deal with 900 degrees C, you need to deal with fluoride, you need to deal with many kind of depositing precursors like silane, forming silicon oxide layers on your, so the efficiency of your reactor will be always impacted by that. So difficult task. So but one of the tasks, each solution could provide a substantial improvement in the semiconductor industry. The more you go outside, the more it's important that you digitalize your factory. Historically, the process was not really communicating with the facility systems, but the more information you can provide, what is actually your use in the inner part of the fab, the better you can optimize the operation of your outside components. This is something ongoing in the moment in factories. So innovations in that field, how you can make, for instance, an RF generator capable of running at different loads, or how you can improve the recovery or the startup time of an ozone generators. Yes, that would be also ways of how you can improve the energy efficiency in your factory. Remember, not everything can be covered by new processes and by new materials, because once you have installed them, and that's another specialty in the semiconductor industry, you pay lots of money to requalify that changes what you're doing in your process to prove to your final customers that you have no impact on their reliability and quality of the final product. So that improvements what you need to have, you should bring in areas where it's excluded that you have any impact on that. So optimizing the idle to sleep modes, that means optimizing the performance, especially in the times when the equipment, when no wafers are produced, would solve that problem. Last but not least, heat recovery, also recycling of things like exhaust. Also, your air could be recycled. Here we see the water recycling, chemical recycling, waste recycling. These are means what you can achieve in the facility side. And this is where the big opportunities are today. In the building side, energy efficient building, renewable energy has been covered in the presentations before. Here, one comment to Catherine. So actually, we are already better than you think, because you see here, this is from the TSMC, the last CSR report. So you see here, they already have reached 96% of water recovery, of waste recycling rate. Sorry. So, and the water recovery is a very similar value already there. So this example here shows that actually we have a way, companies, if they're innovative enough, they can achieve very good values in that regard. Important is that you keep and I call it the interrelationships here under control. For instance, when you say, I want to reach from 95 to 100% in my water recycling, then actually your energy consumption is increasing dramatically. Also, what you will do, the waste from 95 to 100% has a lot of solids. So the technologies you're using here are crystallizers and evaporators for boiling in the final 5% of your water. In Japan, actually, zero waste treatment plants have been in use in the semiconductor industry in the 80s and 90s for different reasons. The reason was that the local communities didn't want to get any wastewater from the fab to avoid any potential risk for beta sites like they have been seen in the Silicon Valley. So in Japan, a lot of factories have actually had this zero water facility. There was about 4 or 5 fabs which have that zero water facilities. However, when the energy crisis hit them, that was the first thing they shut it down. So they couldn't afford anymore to have a nearly double energy consumption to recycle water just from the last 90 to 100%. So the same is when you remove the contaminants from the air, like greenhouse gases. You need to be aware, and there's no other chance, when I remove CF4 or NF3 out of air, I'm generating at the end some solid waste because calcium fluoride is the only way. However, when you are doing it smartly, then you can have the CF2, the calcium fluoride waste, in a format what you can resell to a steel manufacturing or to glass manufacturing, and then you can close the cycle. So this is very important. That especially reuse, recycle, reclaim is the key method of solving your eco-efficiency issues. But when you do use that here, you need to both to have the energy, the chemicals, what are needed to do the treatments, and the waste problems under control. So even a simple target is actually in semiconductor often a very complex issue. However, we need to approach them, and we need to use our technologies to make that happen. So to show you here an example how you can use, without impacting negatively the product, that information. So when you build up here your tool, you understand, you basically know at every time, and we can measure down to every 50 milliseconds what kind of gases are used in a certain reactor. From this reactor, the exhaust, as Catherine has shown, is going to pumps, and then from the pump, they go to the abatement. But when I know what kind of gases are flowing, I don't need to run my pump with full nitrogen purge. And I don't need to run my abatement at the highest fuel rate. So I can adjust my fuel rate, my oxidizer rate. In the abatement, I can adjust to the actual gas used in the fab. When I do that in the fail-safe method, that means, as we have methods developed, how there's cross-checking between the individual component, that all the communication is established, you can be quite efficient. You see here, this is an example from a factory in Taiwan. At 582 with that method, we have been able to save 5.1 million kilowatt hour per year in electrical energy. About 1.4 million cubic meter of fuel gas, and the carbon footprint went down by 9,700 tons per year. The cost saving was 2.4 million alone in that factory. So that manufacturer has published it was TSMC. So they are now expanding that system to all of their fabs in Taiwan. And the target is to reach 32 million kilowatt hours per year in the next phase savings, and 8.7 million cubic meter of natural gas in the next saving. So simple things like coordinating between just the pumps and abatement to the actual process consumption can lead to a substantial improvement in your carbon footprint in your fab. At the same time, you can pay for all that improvements for itself by reducing less utilities in that case. And by the way, I've not even listed here the water. Also, the water consumption for the abatement goes down by about 10%. So to summarize, there's a timeline in how you can approach the target to carbon neutrality. TSMC want to reach that in 2025. So they went through the first 3 levels already, and now are going to deeper levels of savings, where you go to higher ROI levels and optimization of recycling and reuse. So we should always start with reviewing your new tool design and new fab design, because you have to live with it for 10 years. And then the idle and sleep modes, that means the alignment, the synchronization between the inside of the factory to the supplementing processes, can provide you already a huge step forward with an ROI of less than 2 years. And then the next steps would be to optimize your facility, implement other actions which are taking more investment, and going then step by step to the carbon neutrality. This is some process we can support you, and there are also semi-standards and organizations. So as I told you, it takes a village, it takes cooperation over the complete industry to make that happen. Thank you very much.
All right, thank you, Andreas. That was a fantastic talk. Thank you for highlighting the sort of eco-efficiency engineering methodologies, as well as some of the specific examples of areas where we need innovation that can really help us improve on sustainability. So that was very fitting for this today's forum. I'm looking at the chat box. There are a couple of questions related to KPI. I guess if you could just highlight a little bit, what are some of the industry initiatives in trying to standardize some of these KPIs so that they can be more transparent and easily comparable across different tools and companies?
Yes, so we have seen in the first 2 presentations already some of them in the ITRS and now the IRDS. Yeah, so we maintain that KPIs for water consumption and for energy consumption, and we also corrected some mistakes. We know single wafer cleaning is very important, so your water consumption KPI is very hard to maintain, but we introduced a second one. The second parameter was the amount of raw water used per wafer instead of the amount of UPW. And with recycling, you could achieve that second parameter better. And that's actually what's interesting for the community. The community doesn't care how much water you're circulating in your fab and what you're doing with it. But they cannot sustain to provide you more raw water from the outside. So when you recycle your water, actually you can meet both. Therefore, we introduced in the IRDS a factor. This is the raw water consumption per wafer, which in my opinion is much more important than the actual water, the UPW consumption per wafer.
Excellent.
So because single wafer cleaning has so many processing advantages, there's no way that people will not do that.
Wonderful. So I think we have 1 minute left. Maybe just squeeze in another question. I know, Andreas, you interact with our customers, the foundries, quite often. What are some of the areas where our customers, the foundries, that are making the most demand for in terms of sustainability-related improvements?
So energy is a big issue, yes, for the foundries and water, because renewable energy is very difficult in Taiwan. The space is not there. The hurricanes and the typhoons preventing also other forms of, and they want to get rid of the nuclear industry, the nuclear power. So energy is the top parameter, and the second is waste. So waste is, again, we need to do something about our waste. It also has the biggest potential. The waste is actually raw material. You need to see the waste as a raw material. And then you can find ways of how to recycle and improve. You see 95% recycling efficiency on waste. That is a real point. right? And this is something they spend up at least 10 years coming to that level. And there's a lot of innovations needed to maintain that level because we permanently change our materials. Yeah, so in semiconductor, waste removal or waste recycling efficiency is a running target. So it's a moving target. So you need to have permanently more innovation to maintain that levels.
Perfect, perfect. Thank you, Andreas, and thank you to all the panelists. That was a fantastic session. So with that, we're right on time to move over to the next session, which is Innovation Showcase. I'll see you there.